It is most definitely working.
Oh, yeah. Oh, yeah. That does not happen.
Anna didn't do it. Everyone else did it. Even Adrian. You stopped mid-sentence.
And Zach is our winner. Congratulations. All right. All right. So we're going to let's begin here. Let's start with number 9. What I want to do, because again we've got this quiz on Friday. I won't be here on Thursday, so I want to get through this. Be talking about the quiz a little bit, but then get started with section 6.3 a little, and then be able to finish that up tomorrow early enough that you have some homework time, be able to ask some questions, kind of those kind of things. And then if you've got questions before the quiz Friday, probably lunchtime Friday, before school Friday, would be times you'll probably need to get some help on that before the quiz on Friday. We're also going to be doing some work in the packet. We want to kind of finish up sample 3 this week before spring break would be good. And so we're going to be doing some of that as our homework tonight as well. That's actually what our homework's going to be, is in sample 3. But anyway, so what I'd like to do here is start with number 9, because number 9 encompasses the very basics of what you need to be able to do really in section 6.1 and 6.2. If you can do these things, those are the basics that you need to be able to do. So it's a good review from that standpoint. So they give you this integral. I, as always, represents the exact answer. First thing in part A is they want you to find the answer using the fundamental theorem. Okay? So we would write that as x to the negative 1/2. So we do the antiderivative, raise that up to a half, divide by half, which is times by 2. So we 2x to the 1/2 from 1 to 4. So we plug a 4 in there. That'd be square root of 4 is 2 times 2 is 4. Put a 1 in there. Square root of 1 is 1 times 2 is 2. So we get the answer of 2. That's the exact answer. That's the exact area. Okay? So you need to be able to do that. Okay? Might ask you to do that in a question or part of a question on the quiz. Next thing they want you to do is compute the approximation error I minus L3. Well, before you can do that, you need what? You need L3. So you need, and that's one of the things we did in section 6.1, and since it's single digits, what do you got to do? Write it out by hand. So you would need to do L3. Now, in discussing this with some people, it is probably when we get to the test in test mode, you will not be able to use your area document, which is fine. All the area document does is find like L10s and R20s and T30s and that kind of stuff for us, so we don't have to do them by hand. But I don't care. I'm not going to ask you a question just what's T30, where you just do the area document and just write down the answer. I'm not going to ask you that, but I might ask you a question where you need a T50 to finish out the answer, like to find the approximation error or something like that. Well, if that's the case, I'll just give you T50, right? If you need it in the problem, I'll just tell that to you in there. But you cannot go to you won't be able to go to your area document to do, say, an L3. Well, an L3 you've got to do by hand anyway. So if that was within a problem like this, it would be expected that you would do L3 and you would write it out by hand. Now, there's only 3 of them. You can do it however you want, but the way we've been kind of doing it in this chapter is this, right? Writing it out this way, okay? Now, when it comes to trapezoid or Simpson, you have these shortcuts. Well, they're not really shortcuts because in this case, you'd have to do L3 and R3 to find T3. So they're just other versions, other formulas that you can use. Okay? All right. So on this one, so we had L3. So that's going to be B minus A over N, which tells us our width is 1. And so if these are lefts, we're going to start at 1. So we have F of 1 plus F of 2. And this is kind of the slacking part I was talking about. Now, not so much on this one. I think on some of these earlier ones, a lot of you had this written out. But you should have that on your paper. Now, you don't have to do the F notation if you don't want. If you wanted to actually plug those in directly, plug in a 1, that would be 1. Plug in a 2, that'd be 1 over root 2. Plug in a 3, that'd be 1 over root 3. If you had that written in the parentheses instead, that's fine. and then you should go ahead and type that into your calculator. Now, one of the things we did in section 6.1 was we put this as we defined our function to be this, defined f of x to be this, and then we just typed in the f notation. That's fine. We should probably give a decimal answer on this. What was it? 2.284. Okay? If you give the exact answer, it's just 1 plus root 2 over 2 plus root 3 over 3. I mean, which isn't all that telling about what's going on. So I really kind of prefer decimals here. And so 3 decimal places would be good. All right, and then we do an R3. So that would be very similar, b minus a over n. Except we don't use 1 this time since we're doing rights. And since the width is 1, our first one would be at 2. And then it'd be at 3. And then it'd be at 4. Okay? And so we would have that. And when we work that out, it comes out to be 1.784. Okay? And then you have to do your I minus L3. You have to find how much error is there. Well, that'd be 2 minus that, so that'd be 0.284. And your I minus R3 would be what was it, 216? Is that what you have there? Okay? So those are all things you need to be able to do. So number 9 was a really good one. I mean, if there's one question you could do that would review a lot of the different components of what we've been talking about, this is it. Okay? So that was part A, or that was part B then. We're not quite done. Are these errors consistent with the error-bound formulas in Theorem 3? Justify your answer. Well, your work is kind of your justification. So, I minus, according to the Theorem 3, and I won't say Theorem 3 on the quiz, but I'll say, the question will say use the formulas above or something like that. So you'll know you need to use these formulas. Okay? So we had the formula for a left. It's the same formula for a right. Okay, there's our K1 value is going to go in there. Okay, we got 4 minus 1, what was that, squared? All over 2n. So that'd be 2 times 3. And K1, of course, remember, K1 is the max of the absolute value of f prime. So get ready to go here, Zach, and let's put in our, do your derivative for this one. Do your derivative of 1 over square root of x. And let's remember how we do this K1. So as he's doing that, so we go up here, so he does his derivative of our function, that's that. Let's copy that. We're going to copy and paste, we're going to graph that. Okay, let's get that one out of there. Now, we could talk about number 29 today. Or was that number 29? Yeah, I think that one he has there. But so he does his absolute value. He's going to paste that derivative in there. We're going to look at it. We only want to look at it from 1 to 4, so he's going to set his window from 1 to 4. We're going to do, now Blakely's calculator was acting kind of funny on this, but did it work? Did it end up working the rest of the time? Okay, we just reset it. Now, this is the interesting thing. Now he's going to do a zoom fit. But you notice, you probably without even doing a zoom fit, you can kind of see what's going on here. Okay, where's the max? It's going to be back over here at the left edge. Now he did his zoom fit, so now it's over here. But go ahead and just, he did his trace, I guess. And right there it's 0.5. So this is what we were talking about yesterday. Since it's exact, you don't have to bump it up, right? Because remember what K1 is. We're looking for the worst case slope, the steepest slope that it ever is. And we're going to pretend it's that slope the whole time, right? That's the whole key to these formulas. We're going to pretend it's that slope the whole time. The only time you have to bump it up is if you get a decimal that's an ongoing decimal. It's not exact. So if you want the steepest slope that there would ever be, you need to just round up whatever your last digit is and use that. But if it's exact, we can use that. So our K1 value is going to be 5. Now we're going to do second derivative here in a minute, so why don't you go ahead and do that now so you're ready to go. So we're going to put 0.5 in for our K1. So when you do this, what do you get for your answer? 0.75. Now is that consistent with what we found back here? Why? They're less than that. In other words, this is our max error. That's what this formula tells us. That 3 left rectangles are going to be off by at most 0.75. At most. Okay? Well, they were off by 0.284. So that fits. They were off less, and that's usually the way it is, because remember, when we use this 0.5, we assume that the slope was 0.5 the whole time. And it probably is not in most functions. Going to be that way the whole time. That's what this number is based on. So chances are we're much more accurate than what this says. This says we're going to be within 0.75. Chances are we're within a lot less than that, like in this problem. But this is a guarantee. We're guaranteed to be within 0.75. That's what's important about that. Because remember, the only way we were able to get these numbers is what? Well, no. What was the key to getting this number? We had to know the exact value. And sometimes you don't know the exact value. So in this problem, we're just kind of double checking is what we're doing, right? We would not have been able to know how much we're off without knowing the exact value. So this is the more useful one because this tells us, hey, we know you won't be off more than that if you do an L3. R3 would be the same thing. Okay, then you go to part C and they talk about midpoint trapezoid. Now I don't want to go through all of that again, but it's the same thing, just different formula. We have K2 this time, which is the max of F double prime, and you go through all that. And I don't know, what did you come up with as your max on that one? That's what you got for the K2 value. K2 was 0.75, and then when you work this all out, it was how much? 0.5. Okay, let me double check here. I don't remember looking that up last block. That was in C. Yeah, point. Where's it at? Point. Oh yeah, you got like point. See, I'm showing something different here. It's over 12n squared for trapezoid and 24n squared for midpoint. Oh, okay. See, they've got the midpoint one in my book here, 0.18750, or for trapezoid. And for the midpoint, they've got 0.09375. That's what the formula gives you on that one. And that's using 0.75 as your K2 value, right? Now let's show that that actually is the K2 value. Let's do part D. Part D then, this is another thing you need to be able to do, and that is how many midpoint rectangles do I need to guarantee that I'm within 0.005. So that would be 4 minus 1. That would be cubed. This would be 24n squared. And we want that to be less than or equal to 0.005. And so right here I need the K2 value, which is the max of F double prime. So back to the calculator for Zach. He's got our second derivative plugged in here already. Okay, and it looks a lot like the first derivative. He's got our second derivative in here from 1 to 4. Where's it max? It's back at the left edge, so we just trace at 1, and he's got 0.75. So that's where you guys were getting that 0.75. Again, it's an exact value, so we don't have to worry about bumping it up. And so that's where you got that value. Now this part, we can just solve on our calculator. So go ahead and do that, Zach. So we can just type that in and do a solve on that. And you should come up with, see what he gets here, 7.5. Yeah, 4 minus 1 cubed over 24n squared is greater than or equal to, less than or equal to, what just happened? There you go, less than or equal to 0.005, comma x, so we just solve that equation, and we can ignore the negative one, and so it's greater than or equal to 12.99, so we would put 13, right? Now, you could have, the question was how many, find a value of n that guarantees you'll be within 0.005. Well, you could say 20, right? Technically, that'd be correct. That would guarantee you'd be within 0.05. Any number greater than or equal to 13 would work, but I think your answer should be 13, right? That's the best, because that'll guarantee, we always want to do the fewest. If you had to do these out by hand, you wouldn't want to do 20. You'd want to do 13. If 13 will do the job, you'd want to do 13, right? Because that's guaranteed to get us that close. Okay, so that was part D. So those are all the things you need to be able to do with the theorems. The basics right there, number 9. Be able to write out some stuff by hand, you know, so forth, so on. All right, let's take a look at the next one I wanted to do. Okay, I already did that. Okay, let's talk about 27 here. Now this is the one when I was going around looking. Speaking of that, Brian. Okay. So when you get to number 27, so this is the part I was talking about because a lot of you, it looked like you just kind of taken some things maybe from the back because you have got to, when you're using the Theorem 3 formulas, you've got to show that work. You've got to have this on your paper. So I know we're doing a lot of this in the calculator, but not everything. I mean, so like on 27 in part A, it says, what's the smallest value of n where this will be within 0.005? So we're going to have our k1 value because it's left, so we're going to use k1. 11 minus 1 squared over 2n, and we want that to be less than or equal to 0.05. Okay? So, Zach, hopefully you're working ahead of me here. That'd be good. So we're going to do the derivative of this guy right here. We want the max of f prime. Got your work cut out for you here. Look at that. He's doing a great job. He did his derivative. He's going to copy and paste that. We're going to do the absolute value of that. Do the absolute value of that f prime. We're going to look at it from 1 to 11. We're going to zoom fit it so we can see all the. Now this is the key to number 27. This now is when we're going to start getting into some situations where on the quiz, some questions that really are going to show if you understand what it is we're doing, not just the basics, which is what number 9 was about. Okay, so now clearly the max is where? At the left edge at 1. So we go to 1 and we trace. We got 0.841471. Now what should we use? 0.8415 would be okay. I think 0.842 is okay. I think if you go 0.85, that's getting a little too maybe round too much, but not bad. That wouldn't be bad. If this was 0.849, I'd feel better about using 0.85. But if this was 99.84, then I think I'd just go to 100. Because that's not that much rounding. But when you're at a small number like this, going to 0.9 I think would not be good. So 0.842, let's use that. Let's use 0.842. I heard that number. So let's use 0.842 as our K1 value. Okay? All right. So we go ahead and we solve this, and what would you get? 8,000. Well, okay. Now it's not 415. Yeah, okay. It depends what you use, doesn't it? Right. So people are going to get different answers. This is one of the things. This is why this has got to be on your paper. Anytime we use these theorems on the quiz, I'm looking at this and I'm looking especially what you put for that number. Okay? You're getting graded mostly on that. That number is then going to determine what this number is. So if I use 0.842, then yeah, I think Allie said it would be this. If you used 8415, which is what the back of the book used, then it'd be 8,415, right? Because the closer we can get, and that's why we want to pick as close a K value as we could. What if we use 0.9 here? Well, it'd be 9,000, right? And so we would have been saying that we need another 500 and some rectangles when we really don't, right? And it's because we rounded that, right, more severely. So I think that's a reasonable number, okay? So 8,420 rectangles will do the job. Now, as it turns out, 8,415 would actually do the job, but what the heck, it's only about 5 extra. Now, in the other class, it was kind of funny. I hadn't done this before. I had it, so I'm saying, okay, what they're saying is we would have to do an L 8,420, and we would be guaranteed to be within 2 decimal places. So we tried that in the area program, and it just kind of crashed our calculators. I mean, the calculator just spun and spun and spun, and you could break out of it. But then a couple people just let it keep going, and finally, towards the end of the period, a message came up that said resource exhaustion. Something can't be found or something. So I didn't know calculators could get tired. But evidently it just, whatever, the program just was going for too long and it timed out or something. So it never actually did it. But here's the reason I wanted to do it. Because here's the exact answer according to our calculator. And what I wanted to show you is that 8,420 rectangles is guaranteed to be within 0.005. But probably, if we actually calculated 8,420 left rectangles, I'm guessing we would be within about 5 or 6 decimal places. I think it would give us way more accuracy than we needed. Well, that's what parts B and C were about, actually, and D and E. Okay? In other words, this is a worst-case scenario. Now, what is it about this F prime graph that makes me think that? Go back to the graph there, Zach. Yeah, zoom in again, or do your 1 to, just set your weighting settings from 1 to 11 again. So it flattens way out, which tells you what? Not only do they not change, but go out here at about 6. So 0.84 is not a lot of slope. I mean, it's about 1. Now, 45 degrees, so I guess that would make a left rectangle be off quite a bit, right, if it's 45 degrees. But look, trace at 6. Yeah, once you get out here to 6, there you go. Once you get out here to 6, look at the slope. Yeah, it's basically flat. How much error is there in a left rectangle? If it's flat? Hardly any, right? If the graph is flat, the left rectangle fits it really well. So out here, those left rectangles are committing almost no error. So if we did 8,420 of them, we should be getting a pretty good approximation. But what is this formula assuming? You're right? We're taking that 0.84 number, which is the graph, and this is why this is the example they chose, because it's so extreme the way it does it, that we're using this number up here and assuming that the slope stayed that the whole time. And it doesn't. Okay? And so when we say we need 8,420 rectangles, we really don't. So that's why I wanted to get that number. I wanted to see what this was, because my guess is it's a lot closer to the exact answer than this theorem is telling us. But remember, and it doesn't mean the theorem's bad. It just means the theorem is limited by this piece of it. But it's still going to guarantee, if we do that many rectangles, we will be within 0.05. Okay, now here's the next part. So part B says, okay, what if you did the integral from 1 to 6, and then also the integral from 6 to 11? In other words, do what to it? Split it up. And since most of the error happens where? The graph's still up there, Zach? Most of the error happens where? 1 to about 3 or so. But they just say, let's split it in half. So from 1 to 6, that's where the slope is the steepest, because this is the F prime graph, so these numbers are bigger. That's where most of the error is. The last part, there's hardly any. So what they're saying is, let's take the amount of error we're looking for, which is 0.005, and let's split it into most of it let's put in the first part where most of the error is, and the rest of it let's put in the last part. And then let's add those two together. So we go ahead and we do our thing here. So we have our, what would be our K? Same thing, right? From 1 to 6. The max was over there at 1. So that'd be 0.842. We'd have 6 minus 1 squared over 2n less than or equal to 0.004. So that's, see, this is what I wasn't seeing on most of your papers on number 27. I wasn't seeing these different formulas written out. You should have this written out in part A. You should have this written out in part B. Okay? Part C, we should have, what would be our K1 value for that one? You still got that number? No? Yeah, wouldn't it be here? Because from 6 to 11, it's going down, so the max would be back at 6. So 0.00461, I think, would be a good number to use. So 0.00461 would be our K value. And then we'd have 11 minus 6 squared. We'd have 2n less than or equal to 0.001. So when we solve these, this one comes out to be 2,032, and that's where most of the error was. And here it comes out to be like 58. I think with that number, I think it's 58. Well, that's a heck of a lot less than 8,420 rectangles, right? So what this is saying is, hey, in that area where there's most of the error, if we do 2,600, we'll get within 0.004. And the last part, where there's hardly any error, because it's very flat, it only takes 58 rectangles to get within 0.001. See, so a problem like this really makes you think about what is going on with this formula. So I want you to be able to discuss that and answer questions about that and understand what's happening. Okay, now, when you talk about D and E, it says show that the estimates computed in B and C can be combined to produce an estimate that's guaranteed to be within 0.05. Well, that just means if you add these two together. If you add this together, you get the integral from 1 to 11. If you add these together, you get 0.05. That's all that D is saying. And then E says the values in A or D are both estimates. How does the amount of computational effort necessary compare with Part A? Well, it's a lot less rectangles. Part A was 8,420 rectangles. This is only about 2,700 rectangles. Takes a lot fewer. And we still get the accuracy we need. Now, the hard part was we had to split it up more, right? We had to spend time splitting it up and that kind of thing. We could even do less if we needed to. But again, it's big picture about the theory and where these formulas come from that I'm really interested that you understand. All right, so the key element of this then is for left and right rectangles, it's a steepness that determines it. And so that's F prime. So we look for the max of F prime. That's what K1 does. And then we assume it's a worst case scenario. So we assume it has that slope the whole time. That's what tells us how many rectangles would be needed to get that accuracy. Trapezoids and midpoints, it's what that determines the error. Second derivative, because that measures concavity, how curved the graph is. So it's all the same things we just talked about, except applied to concavity as opposed to steepness. Okay? And so those formulas tell us how accurate midpoint and trapezoids would be. All right, so I said I wanted to talk about 29. On 30, let's just talk about 30 real quick. 30 was one where they just gave you the graph, but they forgot to put bars around the F prime, because that's what the graph is in 30. They didn't put bars around it. So what number would you use on 30 as your K1 value? 10 would be okay. 9 maybe, right? Because if you look at the picture on 30, you want the max of the absolute value of F prime. Well, they give you an F prime graph, but it's negative. Well, you don't care about the negative. Right, the max would be down there around 9, positive 9, because if that was absolute value, you'd flip that up. So that's the only difference in number 30 was that. Okay, so let's talk about, oops, not that. Let's talk about number 29 real quick. 29 said the integral from 0 to 2, square root of 4 minus x squared. Now you're going to get your calculators on this quiz, but it would be good if you knew what this graph was. It's a half circle centered at the origin. That's what it is. It comes from x squared plus y squared equals 4. That's right. You really need to know that. You know, when it comes to the final and the package, a question like that's going to be on the no calculator part. You really need to know that that's the top half of the circle, radius 2. Okay? So, if we're looking for this area, okay, they tell you to do it exactly. Well, there's no antiderivative. You can't do that. This is a geometry one. Yeah, it's pi r squared divided by 4. Be a fourth of a circle. And the radius is 2, so that'd be, oops, pi r squared. That'd be 4 pi over 4. So that would be pi, right? So the area that we're talking about is that area right there. That would be pi. Okay? Then it says, so that was part A. Part B, what's I minus L10? So you can go to your area program, you can do L10, subtract it from pi, and you get that amount. Why doesn't Theorem 3 provide a useful bound on the error? If you do the derivative of this, it goes up exponent, there's an asymptote there, right, at 2. There is no max. Well, it makes sense because what's the slope? What's the slope right there? It's a vertical tangent, it's undefined. There's a vertical tangent right there on a circle. And so it's undefined. And so there is no max. And so theorem 3 doesn't really work. Okay, because we can't find the max. So that would be the only limitation on these theorems is if you can't find a max of f prime or a max of f double prime. If we wouldn't have one in that interval. Okay, so it doesn't really work for you. All right, so that's just a little bit of understanding what's going on with that. All right, questions about any of that stuff?
So, since it's undefined, what do you technically have to do with x approaches 2 and on the derivative?
As far as like a number to put into the formula,
That's infinity.
well, it'd just be infinity though, that's the problem. You know what I mean? The limit as x approaches infinity would just be infinity, yeah. So there's just no number you can put in there. I mean, there's no, because K1's supposed to be the most slope it could be. There's just no number to pick. Yeah. So basically you would just say theorem 3 doesn't apply. Yeah, we can't. What was their wording? They said, why doesn't it provide a useful bound? I mean, I suppose we could pick a really big number, but then it would just say, well, you need this many million rectangles. It's just not gonna work. Okay? All right. So anyway, I'll probably provide a list. I'll probably post it on our website with the, review this, review, for the quiz. But really, this stuff is 6.1 and 6.2. I mean, 6.1 was really just about these, kind of getting these things and doing them by hand, okay? And Simpson and trapezoid and stuff like that. So you need to kind of go back and do those. Make sure you can do those. We did a couple of them today. Or use these formulas. So you probably need to practice those a little bit. And we can talk about that a little more tomorrow. And then, and then this 6.2 is really about these formulas here, okay? And you don't have to memorize these. You need to know what K1 is, and you need to know what K2 is. I probably won't have this on there, okay? When it comes to the quiz, I won't have this, and I won't have that, okay? But I'll have this and this, okay? So you got to know what K1 is, you got to know what K2 is, you got to know how to find it, and then when you're using them, you got to show your work. You got to show me this. So I can see what number is in there, and you're getting really graded on did you pick the right or a proper value that goes in there. Okay? All right. So let's talk about this right now. Let's switch gears here a little bit. While you're getting your notes out and kind of getting organized here, I'll kind of explain what we're gonna be doing here a little bit. All right. So we've got one more section to do here in chapter 6. It's called Euler's method. Euler's how you pronounce that. Euler. Okay? Or Euler if you want, but it's really pronounced Euler. Now, it seems like kind of a shift of gears. It says Euler's method is a method for numerically solving differential equations. So it is, in one way, it's very different from what we've been doing. Which seems kind of strange. Why would they throw this in chapter 6 when it's not really related to what we're doing? But as you'll see, there are some things about it that are very much connected with what we're doing. Okay? But first the differences. We've been working with integrals and area and approximating those things with rectangles, trapezoids, and so forth. Here we're talking about solving differential equations. So that, in one sense, that doesn't have anything to do with what we've been doing. Doesn't have to do with integrals, doesn't have to do with area, and so forth. Okay? But how we go about doing this, you're going to see, is very, very much related to what we did with our approximations for area. All right, so it's a method for numerically solving differential equations. So what I want to do today, we're not going to go through all of this. We're not even going to do homework on this today. But I want to get enough of a head start on it so we can get into it tomorrow, finish it up, and give you time to work on it. Okay? So I want to get a head start on it here. So first of all, what's a differential equation? Equation that has derivatives in it. What's the solution of a differential equation? The original function y. When we solve a differential equation, we're trying to find the original function y. Now, we have already talked about solving differential equations. Let's review. Slope fields are a graphical method for solving differential equations. Now, it's just an approximation, really, and so is Euler's method. So there's a similarity right there. These are approximations to the solution, which is what we've been doing for integrals. We've been approximating the solution. So from that standpoint, you can kind of see why this would fit in. Now, here are some examples of differential equations. Y prime equals 3y. Y prime equals 3x plus 2. Y prime equals 2y minus 3xy double prime. Those are all differential equations. They're equations that have derivatives in them. Now, some of these we can't solve. Like this one, we don't know how to solve this yet. This one way over here, we don't know how to solve that. But we do know how to solve this one, right? What would we do? Antiderivative. That'd be 3 halves x squared plus 2x plus c. And to find the c, we need some initial condition. We could plug in, we could find our y value. So if we solve a differential equation, we get the original function y, and then we could find some points on that particular function or that particular graph. So some of them we know how to solve and some we don't. So if we don't know how, it's just like area. Some of them we can do fundamental theorem part 2, and some we can't. Well, the ones we can't, well, we can maybe approximate the answer. Well, that's what we're talking about here. So on these, maybe we could approximate the solution if we don't know how to solve it. Well, one way we've done it is slope field. So let's review that real quick. You wouldn't have to draw this out. I don't care if you draw this out right now. But let's take this one that we don't know how to solve it. Now, we were supposed to kind of memorize the solution. Remember that? A e to the kt. So the solution to this actually is y equals a e to the 3t. Now, later in chapter 7, we're going to learn how that comes about. But for right now, let's just pretend we don't know what it is. So a slope field was a way of graphing using just the slopes. So what we did is we plotted some points. So we could put, say, a 0 in for y. We get y prime equals 0. Well, that means the slope is 0. So whenever y is 0, which would be down here, the slope would be 0. So remember we put these little dashes in here? Okay? And what about when y is a 1? The slope would be 3. So, well, that's pretty steep. So up here when y is, that's not very good. They're supposed to be going in a horizontal row here. But anyway, when y is 1, we're getting a slope of 3. Pretty steep. Let's put another nice number in. What about when y is 1/3? We'd get a slope of 1. So down here, when y is 1/3, we'd be getting a slope of 1. Something like this. Right? And we could go along and we could keep doing this. And then if I gave you an initial condition like this, we could just kind of go with the flow, and sure enough, we would see that, yeah, that's an exponential equation. Right? And if I gave you a different initial condition, we'd get a different thing. But now, that's a really rough approximation, because how trustworthy is that? If I ask you to tell me what y of 1 is, how trustworthy would that point be? Right? I mean, think about how we got it. I just kind of drew these things in here that were really guesses at what a slope of 3 would look like. And then when I drew this line in, I was really guessing. I was just kind of trying to go with the flow. So it's a very rough approximation. Kind of like left and right rectangles are pretty rough approximations, but then we did midpoints and trapezoids, those were better. Okay? Well, here's what Euler's method is going to be. Euler's method is going to be like slope fields on steroids. It's going to be like taking the idea of slope fields, but really doing the calculations to get a better approximation, instead of just kind of putting these things in and just drawing kind of a sketch. We're going to actually plot some points. We kind of plotted points here, but then we just did these slope segments. We're going to actually plot these points along the way. So that's what Euler's method is. All right, so I've got a little bit of a PowerPoint here